So, now we are going for the third problem of the tutorial 1. So, here the problem is that again we have the noisy signal, that is ECG, sampled at 1000 hertz, and we are trying with Butterworth filter, the low pass filter, to actually remove that high frequency noise. Okay. And we have here 4 different options that we look at, the different options of the that. First is order 2, cutoff frequency 10 hertz, that means order is low, that means it will have a smooth transition and cutoff frequency is also very low. Second is we have model order increased to 8 and that the cutoff frequency is also increased to 20, then keeping the model order same, cutoff frequency increased to 40, then 70. Okay. So, cutoff frequency is increased means in a low pass filter that we are allowing more and more high frequency part. So, we have to see that how it helps to preserve the signal component, that is ECG signal in hand, and how it is successful in blocking the high frequency noise. Okay. So, that is the task at hand. So, the next instruction is compare the results using each of the 4 Butterworth filters individually with those obtained by synchronized averaging. The synchronized averaging, it has been taken as a gold standard in this case, and for that we would like to see that how we can actually get the output. Okay. Next is we would compute the signal to noise ratio, that is SNR. We would compute the SNR here of the above cases, considering the best output as the reference signal. So, we will take out of the 4 cases the best one as the reference, with respect to that we will compute the SNR. Okay. So, the first is we need to get the signal. So, for that we have the signal given here, okay, and here we have got the code. Now, again we remind you that we need to keep the input signal and the MATLAB code in the same directory. Okay. So, with that we proceed. So, now the first thing as a part of the solution is to look at the basic structure of the Butterworth filter. Okay. So, Butterworth filter of order n, here is the formula. We are getting the signal, that the magnitude in the frequency domain of the signal, okay, for a nth order filter. So, that low pass filter we get, and we make use of actually MATLAB, we get the help of it to compute this, the Butterworth filter, and that makes the task easy for us. So, first we need to look at the input signal with high frequency noise. So, we know now, by now we know the game, that what we have to do. First we need to load the signal in a variable, here that variable is x. then we need to note down that frequency of sampling Fs, then take the length of the signal, that means how many samples are there in that signal, and with respect to that we can actually calculate the time axis. Okay. How do we do that? We compute the number of samples. So, it will look like a ramp, the index is increasing, and multiply with the 1 by frequency, that is sampling frequency, 1 by sampling frequency will give us the sampling interval. Okay. And then we create a pen by this figure command and then issue the command for plot. Okay. So, we get this plot here with sufficient amount of high frequency noise. So, this is the signal we need to clean with the Butterworth filter, okay, or low pass Butterworth filter. So, let us proceed towards it. So, first let us see how the magnitude and the phase response of the Butterworth filter looks like. Okay. So, we have the advantage of MATLAB, it is already implemented. So, to use that we need to keep few things in mind, that we need the sampling frequency, that is one variable. Next is the cutoff frequency. The first choice was that cutoff frequency should be set to 10 hertz. So, we set Fc, the cutoff frequency variable, as 10, and the model order should be 2. So, we have taken a variable n to provide the model order of the Butterworth filter, and then we issue a command butter, which will provide us the numerator coefficients and the denominator coefficients for this IIR filter. Okay. So, it is not a FIR filter. So, we need both. So, for that the variable we have given, the first variable is the order of the filter. Next we are giving the cutoff frequency as a fraction of half of the sampling frequency. Okay. That means, if we look at the graph, that both side, if we take the normalized actually frequency, that it is minus 0.5 to 0 and 0 to 0.5 in the right hand side. So, to take care of that fact, we are taking half of the sampling frequency, and what part of that 0.5 that cutoff frequency is, we are taking that fraction, and then the last command low, it is suggesting that we are looking for a low pass filter. Okay. So, you can get these things much better and in more detail if you issue the command help. You can look at the manual of MATLAB, and that plot of magnitude and phase. For that, first we create that pen with the command figure, then like the previous case we have used the command that FREQ Z, and we pass these variables. First is B is numerator, that polynomial coefficients, A is the denominator polynomial coefficient, L is the number of samples we need, that we are giving as the same as the number of signals in the time domain, but it could be some other value, it need not be same as the number of samples in the time domain signal, and Fs is that sampling frequency. Okay. So, that is the command actually we are using, and with that here we get the two things, one is frequency as well as the phase. Okay. Both we can get in the form of plot, and we have given it in the figure here. What we get, that cutoff frequency is 10, that means somewhere here. Up to that the amplitude is constant 0 to 10. After that there is a very slow decrease, that means the transition is not very sharp, and the model order is actually, filter order is responsible for that, we have only order is 2. Okay. And the phase, it has some discontinuity at that part and then it is constant. Okay. Nothing much to note in the phase part. Next, we look at that it more clearly in a bigger way, we see that magnitude and the phase plot, and then we would change the cutoff frequency and the order, go for the second case where we have the model order is 8 and the cutoff frequency is also increased. So, with the increase with the cutoff frequency, we see that we can see this constant portion more clearly, and it has come up to say 20 hertz. Okay, it is constant up to that. After that there is a decrease, and the decrease is more pronounced. Okay. If we look at that at 400 hertz, what was the decrease? If we go to the previous case, we would be able to appreciate that. Okay. That it was actually less than, it was more actually less than 50, the decrease in the previous case when the model order was 2. Now, though the cutoff frequency has moved towards the right, the decrease is much more pronounced, and I think it is about -100 here. Okay. However, phase part there is not much thing to note, but only thing what we can get, the knee position is changing with that cutoff frequency. Okay. So, that is the change. Now, then the third one is that we have the cutoff frequency at 40. So, it has moved here up to this point, okay, that it is constant and then it is decreasing. So, and then we go for that cutoff frequency 70. So, it is coming up to this point constant, and that we will see that there is some impact, that probably it has gone little less than, little higher than -100. So, as cutoff frequency is moving right, that suppression is not that prominent, but the model order has more impact, that we can get. Okay. And the knee point also, that from where it is becoming constant, that is also moved, that is come near the 70. So, these are the different cases we get. Now, we need to look at that how the output signal is affected by the change in the magnitude spectrum and the phase spectrum of the Butterworth filter. So, for that, first we need to filter the ECG signal, that noisy ECG with that each of the Butterworth filters one at a time. So, for that, here we show the code for one case, that already we have loaded the signal. So, that part is there. Okay. So, first part of it, that loading the signal, then noting the sampling frequency, the length of it and the time axis, that is there, and then we plot that in the top row of the pen using the figure and the subplot command. Okay. So, we use that plot command for that. Now, next part is to calculate the output, okay. And already we have computed the numerator polynomial coefficient and the denominator that polynomial coefficients b and a for the Butterworth filter. So, we make use of that and use the command filter, and the third variable is the input signal, that is noise corrupted ECG, and with that we get the output what we store as output 1. So, we plot that signal here and we try to appreciate that what is the change. Okay. So, as we see here the signal, that the signal looks pretty clean in terms of suppression of noise. This is the case that where our cutoff frequency is 10 hertz and model order is 2, but the signal looks like a little bizarre or distorted. That you can get if you look at that the amplitude of the signal, the input amplitude, say it is varying from -2 to +2, here it is reduced, it is -1 to +1 kind of thing. That is one thing. Another thing, if you just take that, if you assume that no somewhere something is wrong with the scaling, if you assume that then I would request you to look at the relative amplitude of the say R and the T. That gap between these two has reduced. Okay. So, what that signifies, that everyone can have their own interpretation, and then at the end we need to see that from the trend that which one is correct. My interpretation is, because the cutoff frequency is low, we lost a good part of the ECG signal, or the part which had some high frequency component of the ECG signal is lost, and thereby we lost the amplitude of the QRS complex, and that is the reason for reduction of the height of the QRS complex. Okay. So, let us see that, move forward, and here another thing, that after doing this experiment we found that for order equal to 8 and cutoff frequency as 40 hertz, we could get the best result. So, that is taken as the reference signal for computing the SNR in this case. Okay. So, that will come later, that, and let us see that how the outputs that come. So, first case, we have taken the Butterworth filter with cutoff frequency 10 hertz and model order equal to 2, and with that when we compare that low output the Butterworth filter, we see that SNR is 8.57. Okay. So, it is not a very good one, and we look at that next case, that frequency is that we have that 20 hertz and model order is increased. We see there is an increase in the that QRS complex value, it has become more than 1, which was about 1 earlier, and SNR also is improved. Okay. Now, we get that the cutoff frequency 40 hertz and model order 8, we see that some undulations are there, and probably they are the details of the signal, and signal has got actually the amplitude. If you look at the amplitude, here it is about 2.5, here the same height it has got. Okay. So, that the lower side amplitude also we get the same thing, that. So, we can actually tell that this is closest to the original signal, and that is why we have taken that as a reference. Okay. However, we find that the details part of that thing is there, and the undulations that is there in the signal, that is not of that high frequency. So, we actually assume or accept that as a part of the signal. Next, we move for cutoff frequency as 70. Okay. A big jump, model order remains the same as 8. In this case, what we find that there is not much change in that signal height, though it may look a little better and probably more closer to the QRS complex is close to the original signal, but a lot of noise is creeping in. But still it is better than probably that cutoff frequency equal to 20, and SNR also tells us the same thing. Okay. If we go back, we can see that the reference signal and that the previous two values, that it was about 8.5, then near 12, then reference signal, that is, and now it is becoming 16. So, it is better than that, but we get the high frequency noises that are creeping in, because we are getting a lot of undulation there in the signal, and that is the reason we have chosen the cutoff frequency 40 is a better choice, because in this case, though we are preserving more high frequency component of the signal, we are allowing part of the noise signal to creep in, which is not a good thing to do. Okay. So, that is why we do not take that cutoff frequency 70 Hz as a good choice or the right choice. Now, let us compare with that synchronized average output. Okay. So, synchronized average output, what we got, first thing we get that we have just taken a cycle. At the top we have the noisy signal, here in the middle we have the Butterworth filter output, and the below is the synchronized average output. Taking that as a reference, we are comparing, and we have that cutoff frequency 10, model order equal to 2. For that we see the signal is very smooth, that means noise suppression is very effective, but we lost some part of that high frequency part, and that is evident here looking at the QRS peak, that is becoming evident. Okay. So, now let us go for the next case. We get the next part, that is the cutoff frequency is moved to 20 and model order to 8. Again suppression is, we would say it is very good, same as the synchronized average or maybe even better, smooth signal we are getting, and there is some improvement in the QRS complex shape, the height has increased, but still it is much further and wider compared to the original QRS complex as well as the synchronized average. Okay. Now, we are going for that part where we have taken it the reference, that is 40 Hz cutoff frequency. There we see that now the synchronized average output, that QRS complex and that Butterworth filter output, they looks very close. So, that is the reason we have told that cutoff frequency as 40 and the model order of the Butterworth filter order as 8 is giving us the best signal. Okay. So, as if we proceed further, we go for that cutoff frequency 70. Now, we get the smoothing has become impaired in this case. Okay. So, these things would be more clear if we go back through the slides. If we look back, that we see that here that undulations are yet to come, some change in shapes or details are there in the signal. Okay. If we go back further, cutoff frequency is 20, it is very smooth, 10 also it is very smooth. Okay. Now, at 70, though the QRS complex shape, it looks again very good, it looks very close to the synchronous averaging, we are getting lots of undulations in other places. That is, if you look at these positions beyond T, before T, or even the part of the T and P, we see a lot of undulations are there, that suggests that the noise suppression has not been that effective. The cutoff frequency has become too high and the noise are started creeping in. Okay. So, now we would look for the summary of this experiment. So, first thing what we note that the Butterworth filter with frequency cutoff frequency Fc less than 40 Hz gives us distorted output. Okay. Why this distortion? That the component of the signal is lost. Okay. Some part of the signal energy is also lost. Next is that we have Fc equal to 70 has some high frequency noise present, and as the noise is creeping in the signal, it comes in the pass band of the signal. So, we are getting noisy output. So, that is not a right thing to have. Then what we get that the middle path is the best when we have that cutoff frequency is in between, that is we have taken 40 and model order is 8, we get the best result, and for that we have taken synchronized averaging as the reference for us. Okay. So, what we get in this experiment, that we know that high frequency noise can be eliminated by Butterworth filter or low pass Butterworth filter successfully, but we need to be very careful in selecting the two things. We need to appropriately select the cutoff frequency, so that we do not lose part of that signal of the interest. At the same time, it is low enough to eliminate the noise signal. Okay. And we would also look at that model order of the Butterworth filter should not be very low. If it is very low, then the attenuation at the high frequency would be very small. So, for a effective low pass filtering, it should have sufficient model order, and we found model order 8 is good enough for this purpose. With that, we would like to conclude that the problem number 3 of tutorial 1. Thank you.